이제 귀한 강의를 들었다 생각하시죠. 오늘의 강의는 리커버를 할 수가 없습니다. 그래요. 알려줘서 고마운데 지금 이제 10분밖에 안 남았습니다. 절대 저의 의도가 아니었고요. 아깝네요. 네. 자, 어쩔 수 없습니다. So anyway, let's continue. So we have to have engineering compromise between different engineering factors. And now that's the reason why people think that at least currently the best technology would be nanosheet MOSFET instead of nanowire MOSFET. So that is one thing. And let's talk about future technology. And since everybody now understand nanosheet is a good candidate for this structure, so it is really easy to migration from just silicon nanowire to 2D FET, because nanosheet is extremely thin silicon plate and 2D material is extremely thin a new material. So this is quite a natural progress from nanosheet to 2D material. And also there is another attempt like migration from nanowire to another material. If we consider just 1D material, then there is a quite a smooth transition from 1D nanowire, silicon nanowire to 1D material. And what is 1D material in this case? This is carbon nanotube. So maybe you can laugh at me. Oh, carbon nanotube, But so carbon nanotube was really a hot topic when I was a graduate student. So my professor tried to commercialize it for sensor application. So it was about more than 20 years ago. And people realized that, carbon nanotube doesn't have semiconducting, part of it have a semiconducting property and part of it doesn't have a semiconducting property. It is just showing metallic property. So that was difficult to make a CNT transistor. However, now more than 2 decades have passed, and now people have once again getting more serious on CNT FET. So if we can see the future of a device technology, maybe at least in ideal sense, not considering any different consideration, if we consider just the intrinsic part of our channel material, maybe this nanowire will be the ultimate structure. Actually, this one is known to everybody in this field. However, right now, in terms of engineering sense, realizing silicon nanowire is not that much beneficial compared with realizing silicon nanosheet. That's the reason why we are currently in the nanosheet era. So please have a look at this slide. This slide is quite new. Actually, it was announced this January or this February. I'm not quite sure. So this is given by an organization called as IMEC. Have you heard about IMEC? No. So this is a research center located in Belgium, Leuven, and this is a European one, so not for just Belgium, but at the time, so several decades ago, European countries just provided some certain funding to support this collaboration center, research collaboration center. And nowadays, so long time have passed, and nowadays this IMEC is used as some hub for providing the next generation technology. The the main reason why it is working as this hub was physical closeness to ASML. ASML is quite nearby this iMac, and iMac get the prototype of ASML's EV technology. So although EV was quite expensive, but they installed the very first non-commercial version of EV, and they were able, the researchers in iMac were able to fabricate the real device with EV technology. So that was the starting point of surge of this iMac's visibility. Of course, it was quite famous for its beginning, but in my opinion, actually, there was just a sudden jump with the EV technology. And they announced their roadmap. There is a long transition in this semiconductor device technology, guys, to provide roadmap. Roadmap means that there are many companies competing to each other to get better performance, but all of these companies have a certain consensus on the next technology. That is the goal we have to achieve in near future. Near future means that after 3 years, 5 years, 10 years. So they have a long transition to generate a roadmap. And amazingly enough, many of our roadmap items have been realized. So it means that almost always they succeed to meet the goal. Or when it becomes, it is impossible to meet the goal, of course they adjust the goal. So therefore always they achieve the goal. But I think that was quite reasonable. And now let's have a look at the most state-of-the-art device roadmap. Where are we now? We are currently living in 2025, and this roadmap was announced in this year. And where are we now? We are at not this one. We are at N2 node. So N2 is why it is called as N2. Maybe it is inspired by 2 nanometer. So nanometer 2, but so anyway, so this is called as a 2 nanometer technology, N2 node, and its cross section is schematically shown here. So please let me draw once again this cross section a little bit in last way. Here we have gray region or silver region, then this is corresponding to silicon and one other silicon. Here we have bottom, middle, top, and this is the structure. Here we have a source of our transistor and drain, and we just make a two-dimensional cut of this structure. So although we operate it as a single transistor, inside it we have already 3 different top channel, middle channel, and bottom channel. So that's the reason why its drivability is just 3 times, roughly 3 times larger than just a single one. Oh, maybe you can ask me this question. Well, it seems like an unfair way to increase the current. Hey, then why don't we just introduce 4 stacks? Each of them is called as stack, and this one is 3 stack device. And why don't you introduce 4 stack, 5 stack, 100 stack? Then we can just increase the current. Why we are using just 3 stack? Yes, if you can, please do. But you know, fabricating this multi-stack device is in reality quite difficult. So this is their best, current best to have only 3 stack. Of course, they have a good plan to eventually increase the number of stacks, not 3, but 4. But 5, I don't know, because you know there are also other effects which degrade effectiveness of adding one more stack. So currently we have 3 stacks, and each of them is quite thin, like a 5 nanometer or even we are trying to thinner one. And here we have the length scale quite similar to the length of our channel. So it's like about 15 nanometer something. So this minimum length is 15. And effectively, what is the effective length of this one? Actually, you know, here, all of these 4 faces are attached to the hafnium oxide. So simply speaking, if this is 15, then we can say that 15 for bottom, 15, 5, 5. So effectively, it can contribute 40 nanometer long peripheral length. And since there are 3 copies of it, so we can have 120 nanometer for rounding shape. 1, 2, 3. Although in terms of its drawn width, if we are looking at from top of the wafer, so you know this is if we just observe it from this side, actually we will see that this is just 15 and slightly further for our other layers like hafnium oxide and gate metal. But when we consider just silicon, it just looks like one layer of 15 nanometer wide silicon wire. So from top view, we can just draw in this way. It is just 15 nanometer wide nanosheet, but inside it we have more copies, 8 times higher width, because we have introduced the internal structures like this surrounding. That is hidden way to increase our current drivability. From the top view, it's just working as 15, but inside it, it has a hidden width, so that is the way. Okay, sorry about not recording today's lecture material. I think that today's lecture material is lost, not recorded. Sorry about that. So next time I will be more careful, and see you next Monday.
교수님, 혹시 그 방송 끄기 전에 한 번만 이렇게 그 필기 앞에 하셨던 거 보여주실 수 있어요?
여기요? 이런 걸 보는 게 무슨 의미가 있을까 모르겠지만 어쨌든 네.